Hey, welcome back to Math with Patrick. Today's August 21st, and we're solving problem number 233 from the Daily Epsilon calendar. And as with all the problems in this calendar, the answer to today's problem should match today's date. So we're going to get a 21 at the end of this video, hopefully. We need to find the number of paths that go from A to Z that only go up or to the right. So it looks like, for example, we could go up and then right, and then right, and then right, and then up, and then right, and then right. And we have found a path to go from A to Z, only going up and then right. So like what's not allowed is to maybe go up, up, and then another up, because then how else will we get to Z? Other things that are not allowed, pretty clearly we can't go up, right, and then left again. And so this is not a valid path either. But we could go something like this, or something like that, or something like this, or something like that. And as you can kind of tell, it's going to be pretty hard to just count them one by one, because like, what if we miss something? What if we accidentally double count something? Anyways, one strategy that I like for this problem is to change it from maybe like what looks like a geometry problem of like a grid and like drawing things and pictures into a combinatorics problem where we're actually counting the number of ways to do something in a more methodical, mathematical manner. So let's bring it back to actually two different examples. How about? So let's go maybe right, right, up, right, up, right. I can rewrite this path as a series of R's and U's to represent which way I'm going at every step. So for example, I went right, then I went up, I went right two more times in a row again, then I went up, and then I went right one final time. So this like string of characters of R's and U's denotes one valid path to go from A to Z. Maybe let's pick another one. So I'll go up. And how about let's just stack all the rights all in a row, and then we'll go up at the end. So that was up, and then 1, 2, 3, 4, 5 to the right. So 1, 2, 3, 4, 5. And then finally I went up at the end. And essentially what I'm doing here, depending on what path I'm taking, I'm rearranging 5 R's and 2 U's, but it doesn't really matter which U goes where. It's not like these are distinct from each other. It's not like I have like secret subscripts on the bottom here. It doesn't matter that this, like both of these U's are essentially the same is what I'm kind of getting at. They are indistinct from each other. So this question of finding paths that go from A to Z boils down to the question of how many different ways can I scramble 5 R's and 2 U's? Because each different scrambling represents a different path on our grid here. And in short, this is the choose function, and there's a lot of different ways to express the choose function in notation. You could do NCR. The big C stands for choose or combination sometimes. And we could do 7, 2. This asks, with 7 objects, how many unique ways can I place 2 of them? And so NCR 7, 2 is asking the number of ways we can place 2 U's, and the R's just go in the places that we didn't put the U's. Similarly, we could have actually asked NCR and then 7, choose 5, because it's the same question. How many different ways can I place 5 R's in distinct spots when I have 7 options? And then wherever I didn't put the R's, I'll just put the U's. It's not like I have more choices there. The U's just kind of fill in the spots I didn't pick. There's more notation that we could use. Sometimes you'll see them as like these vertical parentheses like this. And all of these mean the exact same thing. Now we got to figure out how to do the computation for this, though. We still need to figure out the number of ways to scramble all these letters. Like the notation is great and all, but we haven't done the math yet. First off, we should think about the ways to scramble all 7 letters, maybe assuming that they were actually distinct. So if I had, say, 7 letters, A, B, C, D, E, F, and then G, we could count the number of ways to scramble all these letters with a factorial. I think the best way to talk about this is like kind of work our way up. Like if we just have one letter, then clearly there's just one word I can spell. It's just the word A. But then if I introduce 2 letters, I have 2 options now, right? I could say AB or I could say BA. And so I have 2 options here. And just as an aside, these are both equal to 1 factorial and 2 factorial. To create the next word with 3 letters, what I can do is take my previous word, AB, and then for this word, I have 3 different spots I could slot in the letter C, and spell a new word. I could do cab, I could do akb, or I could do ebk, and all 3 different spots spell a different word. So for this word AB, I have 3 options from there, and then likewise from the word BA, I could slot in the C here, here, or here. And so I do have 3 different options for that word as well. So ultimately, I can just take the amount of words I have here and multiply it by 3, because for each of the words, I had 3 different spots where I could slot in the next letter. So I'm not going to write all 6 examples, but essentially I have 6 different options, and that's the same as 3 times 2 times 1, or 3 factorial. Just for the sake of example, let's do one more. Let's say I have one of my 6 words, which is ABC. I'm imagining where I can slot in the letter D, and I have 4 different spots I could put that letter D, and in each of those different spots, I am creating a brand new word that I haven't seen before. And so for each of those 6 previous words, they each will have 4 spots for me to slot in the new letter D, and ultimately this is just 1 times 2 times 3 times 4, or 4 factorial. So hopefully that's enough of an explanation to confirm that if we were scrambling 7 distinct letters, we will have 7 factorial different options to choose from. And so now we need to reduce this number, right? I was saying that both of these U's, like there's nothing different about one U than the other. They could be swapped and it's still the exact same sequence, and it would still represent the same sequence of moves of right and up on our diagram. And so to consider the fact that we could swap the spaces for the 2 U's, it's just 2 spots. Like it's either this way or that way. And so I should divide my overall total of distinct words or orderings of 7 letters by the number 2, just to represent like not double counting this as distinct from that. The amount of different orderings we have with the R's is a little bit harder, but hopefully you can trust me that it's just 5 factorial, right? Because we just saw that the number of ways to rearrange 5 objects is 5 factorial. And I do want to divide out the 5 factorial so I'm not like double counting a whole bunch of different options. Like let's again pretend, for example, that all of these R's were distinct. So I could put little subscripts on all of them. And then I could say swap these ones. And then again, in the case where all the R's are distinct, this is a new ordering. And so there's going to be 120, or 5 factorial, different versions of swapping around all these R's. And I want to make sure that I'm considering all 120 of these different scenarios all the same, because there's no difference between all of my R's or all of my movements to the right. So technically this 2 actually should have been a 2 factorial. And so here's our formula. If you wanted to do like the choose function for any old number, let's say maybe NCR of like A comma B. First, we're going to put the factorial of this first number. Here it was a 7. There's a 7 up top. So we would take the factorial of the first number. Then in the bottom, we could take the factorial of, essentially we want both the 2 and the 5. And so one way to write it is that we could just do b factorial right here, because I'm looking at this notation. This 2 is in the spot of that b. This 2 is right here, so that's why I have a b right there. And then this 5 just comes from the difference between 7 and 2. And so for my general notation, I could go a minus b, and then hit that with a factorial. And so this is the general formula for the choose function. And it comes from the idea of first scrambling all of your options and then dividing out things that are indistinct from each other. And so this number right here actually is our answer for today. And let's figure out what this number is. It should be 21. The first thing that I like to do when doing these computations by hand is simplifying the part with the higher factorial in the denominator. Because if we think about 7 factorial as just a product, it's 7 times 6 times 5 times 4 times 3 times 2 times 1. And then 5 factorial is 5 times 4 times 3 times 2 times 1. And then I guess I'll put the little 2 factorial over here on the left side. And ultimately, this 5 factorial just kind of cancels out with all the factors above it. And so we're only really left with 7 times 6 on top and 2 times 1 on bottom. And that really simplifies all of the arithmetic when working with factorials. The numerator here is just 42, the denominator is 2, and ultimately this does give us the number 21 for today. So we probably could have counted out all 21 paths one by one and gotten the answer sooner, honestly, instead of talking about all these combinatorics and the choose function and all that. But I at least wanted to give you a strategy that could work maybe more generally for different problems, right? Because previously, say we did this problem by just merely counting out all the different paths. Well, if I start giving you a different sized grid, then you're kind of stuck, right? You would have to count them all out again, and you don't really have a good general strategy. And so now this way, at least if you can kind of link together the idea of this lattice grid and movements right and up with the choose function and the orderings of these different instructions, then it doesn't matter the dimensions of the grid. You could pretty quickly find your answer by either consulting a calculator or doing the computation yourself by hand. So anyways, that's my solution. Thanks for listening to me talk a lot about the choose function and combinatorics, and I think I'm all done. So thanks for coming along and solving this with me, and I'll see you tomorrow. Bye.